Hi, my name is Justin Pearson. I'm a Wolfram research intern and a graduate student in electrical and computer engineering at the University of California, Santa Barbara. And I've had a lot of success using Mathematica and the Wolfram language, both in industry and academia, and I wanted to share some of that with you. So I made this talk for engineers, and in particular engineering college students, to sort of highlight how using Mathematica and the Wolfram language might benefit you. So maybe a first good place to start is what's Mathematica and what's the Wolfram language? So Mathematica was Wolfram's original flagship product. It came out in the 80s. It was a tool used for symbolic computation. Stephen Wolfram used it for doing a lot of physics calculations. And it's since found widespread use in a lot of technical fields. In fact, not only now is there a desktop version of it, but also an online version where you can use it from a web browser. But there was this problem because Mathematica sounds like you can only use it for math. And so they needed some way to distinguish the fact that the Mathematica kernel, the core computation that has all these industry strength algorithms in it, can actually be used for a lot of things besides math. And so the Wolfram language is essentially this programming language that powers Mathematica. It powers Wolfram Alpha, the website. You've probably heard of that. You can do integrals and derivatives and stuff with it. It powers the Wolfram Programming Lab and so on. So that's the difference between what Mathematica is, a program that you can execute Wolfram language code on. OK. Now, if you're an engineering college student and you've been in the computer lab late at night and people have been talking about different programming languages, you've probably heard people say the following things about Mathematica. I can do symbolic manipulation. So for instance, if you want to solve this quadratic equation for x, you can say solve of ax squared plus bx plus c equals 0, and it will solve for x. OK. It solves math problems, maybe. So here we have an ordinary differential equation, x double prime plus 3x prime plus 2x equals 0, some initial conditions, and dsolve, d is for differential equation. Dsolve instead of solve will solve that differential equation for x of t. Maybe you've heard people say, it shows weird symbolic output. OK, so here's an example. Here's an integral, integral from minus infinity to infinity of sine x over x, and Mathematica says, oh, that's pi. That's kind of a cute electrical engineering factoid. But what if I change that integral slightly, so that instead of sine x over x, it's sine of ax over x? Well, then I get this much more complicated expression here. And at first, it looks kind of weird. If you were expecting the number pi or the number 5 or something, this is much more complicated than that. But hear me out. It's a conditional expression. What does that mean? It says, I don't know what a is. Maybe a is a complex number. Maybe a is a real number. I'm not quite sure. It's just a symbol as far as Mathematica is concerned. But conditioned on the premise that a is an element of the reals, supposing that a is a real number, then this integral has value pi times the sine of a. So sine of a is plus 1 if a is positive and minus 1 if it's negative. So in other words, this is plus or minus pi, depending on whether a is positive or negative, and conditioned on a being a real number. So it's not as simple as 5. It's not as simple as pi. But there's so much more information in here, and it tells you, and Mathematica tells you what the answer is, depending on what a is. So that's pretty cool, I think. Another thing you might have heard is that it's pretty easy in Mathematica to make interactive plots. So suppose I wanted a plot of sine omega t plus phi, where t goes from -4 to 4. And if I just enter that in, it won't quite work because omega and phi haven't been defined. So maybe I can define phi, omega and phi to be 1 and 0 or something, and I'll get a static plot. But what if I want to see what that plot looks like as I wiggle omega or I wiggle phi around? Well, it turns out I can just wrap that plot command in manipulate and give it an initial condition for omega and phi and some ranges for omega and phi. And the next thing you know, I'm looking at this really nice plot where I can wiggle omega around, and you can see that the angular frequency gets bigger and smaller. And here's the phase of phi. I can shift the thing around. So it's pretty cool that just with a single, you take whatever command you were going to do, wrap it and manipulate, and suddenly you have a nice user interface. OK, so now at this point, you know everything that the average man or woman on the street knows about Mathematica. And what I want to show you now is maybe what are some extensions that will make it so you know more than the average man or woman on the street. So the thing about learning a programming language is it's hard. The first time I gave this talk, it was to a room full of freshman engineers of all types, chemical, mechanical, electrical. And it was right before finals week. And I was telling them, hey, I know that you've had to learn MATLAB, but you know what? You should also learn Mathematica. So I wanted to sort of empathize with them. I said, listen, I know that learning a programming language is hard. It's at the intersection of panicked frustration and unbridled rage. this homework assignment is due in 5 minutes, and I'm not getting the right answer even though my code is the same as my friend's. And this is exactly what the professor did, and I don't understand why it's working. So in the intersection of these two things is your programming language of choice. For these students, it was MATLAB. And I was standing before them saying, you know what? In addition, here we are right before finals week, you should also learn Mathematica. So the question that was going through all of their heads was, why should I learn Mathematica if I already have to learn MATLAB? And I had 20 minutes. I had to make a good case for why they should do that. And I'm going to make the case to you. I broke it into 3 parts: money, knowledge, and power. Wanted something punchy. For the money section, I wanted to point out that many schools make Mathematica free for students to install on their personal computers. In addition to having it ubiquitous on all of the campus computers, Mathematica has a really generous license on many college campuses. And if you want to check, you can actually go to the Wolfram website and submit which school you go to, and they'll tell you what kind of license they have. Also, you don't need to buy a whole lot of extra toolboxes. You probably know with MATLAB, there's the base MATLAB, and then there's these sort of discipline-specific toolboxes. And I found a funny website at one point that where the author wanted to compare how many MATLAB toolboxes are in the standard Mathematica, base Mathematica package. And he did the work, and it turns out these 18 toolboxes, which by the way are $1,000 each if you're buying corporate seats for them, these $18,000 worth of toolboxes you get for free in Mathematica. They come built in. And the last thing is, you can try it for free online. In addition to having Mathematica online, where you can use the Mathematica software through a browser, there's also the Wolfram Programming Lab, where you can just try things out. There's a nice little, there's these little hints, there's little paragraphs telling you how the language is structured, how to execute commands, and there's a lot of existing code that you can use as sort of a baseline for your own exploration. So it's a really gentle way to get started in learning a new language, and it's free. So that's sort of the money part. It's free, you don't have to buy a lot of toolboxes, and you can try it with no risk online. So let's talk about the knowledge part. So here's a problem from a class that I used to teach where it was a class, of Intro to Programming for engineering in general. And so this is an electrical engineering problem where there's a circuit, there's a voltage source, some resistors, and some currents are flowing through the resistors. We give the students some equations that relate the voltage and the currents and the resistances. And this was a class where we required that the students use MATLAB. And so this was a MATLAB problem. They had to solve it in MATLAB. And I want to show you how even if you have to do it in MATLAB at the end of the day when you turn it into your professor, that you can still learn a lot. You can still have a heightened educational value of this problem if you use Mathematica to at least explore it a little bit. Here's how. The first thing to note is that this presentation and this code, this is all in a Mathematica notebook. And the nice thing about that is, OK, right away, you get some nice formatting. Here we have, here's a sort of a title, a little subtitle. Here is the statement of the problem that I just pasted in. It's just a screenshot from the PDF of the homework statement. And I have that all pasted into a Mathematica notebook. It's not the case like in MATLAB where you have to write a bunch of code, and then that code executes and you get some answers, and then you have to figure out which answer goes with which part of the code. Everything is right here, nicely formatted in Mathematica. And you can execute all these things. This is a live notebook. This is not some sort of published printout. OK, so here's the problem statement that I just pasted in. And OK, here's the MATLAB answer. You probably know, and I'm just showing you this for comparison's sake, that if you were to solve this in MATLAB, you would have to make a separate file. You would have to, by hand, solve these coefficients in this matrix. You would have to then find this b vector and then do a\b. So you would have to transform your problem from a problem about circuits into a problem about linear algebra, because linear algebra is what MATLAB knows how to solve. Let's see how you do the same thing in Mathematica. So here I've just pasted in another screenshot of the equations. Here are the equations. Here's the actual Mathematica code where I'm specifying a list of equations. They look just like this, and so it's easy. There aren't a lot of copy-paste errors here. And then, OK, suppose I wanted to make the matrix coefficients, but I didn't want to have to do it by hand. I wanted to have a computer pull out the coefficients for me. Well, the Wolfram language has a command called coefficient arrays, where I can specify the equations and the variables that I'm interested in, and it will pull out those coefficient arrays, which are exactly the same as I would have had to do by hand in the MATLAB version. OK, so once I have these, OK, then as you know, in the MATLAB version, you would just say a/b or something, and that would give you a bunch of numbers. But you'd lose a certain amount of physical intuition if you do that. Here's my point. In Mathematica, you can invert symbolic matrices. This is not a problem. And once you invert the symbolic matrix, you multiply by the b vector, and you get this result. Now, people who know MATLAB, they might say something like, oh, you're never supposed to invert a matrix times b. It's much faster to use backslash or whatever. And don't worry, in Mathematica, there's the linear solve function, which is the same as the backslash. So we don't have to explicitly invert a symbolic matrix here. But my point is, when you have the symbolic answer, which is not something that you would get easily in MATLAB, you can get a lot of insight into the problem. For instance, you can see that v appears once in each of these terms here. That means that the voltage is directly proportional to all the currents, which is something that you probably know V equals IR from Ohm's law from circuits. But when you have a complicated resistor circuit, maybe it's not as clear that the voltage and currents would be directly proportional. But indeed, when you see the symbols, you can see that V right there. So if you double V, you double all the currents. That's pretty cool. OK, so now that I have the symbolic expression, maybe I want to plug in some values. Maybe V equals 5 volts, and all the resistors are 100 ohms. This percent means the previous result, and it says previous result, I want to plug in, V goes to 5, R1 goes to 100, and so on. So here I get these numeric results. Now another thing to point out here is that Mathematica can deal with precise, exact, infinite precision rational numbers. So these are all rational numbers. This is the number 1 and the number 30. This is not the number 30 represented in machine precision. So these are all have infinite precision. OK. Now, if I want to make a function, because the homework statement said to build a function to do this, I can do that directly in Mathematica without having to make a separate M file like you would in MATLAB. Here's a function that says find currents, and I pass in the voltage and the resistances, and then I can plug in the specific values, 5 volts, 100 ohms, and there's the rational numbers. If I insist on having machine precision numbers so that I can compare them to MATLAB, I can do that too. The N function just converts rational numbers into machine precision. So the point here is that we did a lot of stuff that gave us more insight into the problem, and we could do the same kind of stuff that we could do in MATLAB. But wait a second. We had to contort our thinking from a circuits problem into a linear algebra problem. Wouldn't it be more direct to say, we have a pile of equations, we want to solve those equations for a particular set of variables? And that is precisely what the solve function is for. If you say solve of equations, so this is our list of equations, and I want to solve it for these variables, what you get back is a list of rules. That's what these little arrows are that say, listen, I solve these equations for these currents. I1 has this value. This is in terms of the original voltage and the resistances. I2 has this value in the voltage and the resistances, and so on. Once you have this form here, you can plug in the same as before. You can plug in 5 volts and 100 ohms, and you'll see I1 goes to 1 over 30, I2 goes to 1 over 60, and so on. It's very convenient because this is actually a way of labeling which numbers correspond to which currents. You didn't have that before. You just had this list of numbers, and you kind of hoped that I1 was the first one, I2 was the second one, and so on. So that's pretty convenient. And as before, you can convert this into numerical machine precision numbers. So the point here is that you get a lot of insight into the problem that you might not have had otherwise. For one thing, you can format your Mathematica notebook really nicely so that you can actually have a single self-contained document when you're all done. So years from now, when you look back on your homework problems from college, you can actually understand what they're saying because it's a self-contained document. You can paste in the problem statement from the PDF. You can have plain text in with the computations. And the inputs and outputs are adjacent. You can have the inputs and outputs are right there next to each other. You don't have to run the whole thing and then look through the entire output file. Most importantly, though, you can directly solve your problem. You don't have to contort your thinking to convert your circuits problem into a linear algebra problem. OK, here's another example where in this knowledge section where we'll solve an ordinary differential equation problem. So here's the problem statement. I'll just summarize it for you. The idea is we have a second order constant coefficient linear differential equation. So mx double prime plus bx prime plus kx equals 0. So as you probably know, this is a mass spring damper system if you're a mechanical engineer, or an RLC circuit if you're an electrical engineer. And there are some initial parameter values and initial conditions. And they ask you to solve this in MATLAB and find the kinetic and potential energies and plot them. So let's see how this would look in MATLAB. Real quick. You probably know that in MATLAB, it's kind of a pain to solve ordinary differential equations. If you are faced with this kind of ordinary differential equation, as you probably know, I'll just go over this real quick, you have to define some intermediate variables that are like the derivatives of the function that you're actually looking for. And then you have to take the derivatives of those things and express them in terms of the original equation. So you're turning the second order system into a vector first order system. And then you have to write this MATLAB function that encapsulates the right-hand side of this vector first order equation in your M file. And then you have to call this ODE solver that has some weird name in these numbers here with this function handle that you passed in with the time span and the initial conditions. So when students are first learning MATLAB and they're learning how to solve differential equations, they think, ugh, why do I have to? This doesn't look anything like the way that they're taught in math classes to solve differential equations. And there's all this rigmarole in order to just solve the equation. And even when you solve it, you just get a list of numbers. You just get the numeric answer of the equation. You don't get any insight from an analytic solution. So let's see how this might be different in Mathematica. Here's the problem. I've formatted things nicely so it's a nice self-contained document. I've pasted in the problem statement. And OK, I'll define the variables. And now, instead of doing all this rigmarole with the vector first order thing, I'll just call dsolve. Here's the ODE, mx double prime plus bx prime plus kx equals 0. Here are the initial conditions. And I get this. This is the exact analytic solution. And it's really nice because you can see there's e to the minus t over 4. And times like sines and cosines. So sines and cosines, these are periodic. This e to the minus t over 4 is an exponential. So it's going to be a decaying sinusoid. And indeed, if you plot the solution, you can see that it's a decaying sinusoid. So this gives you insight into what the solution should look like. You don't have to plot it first and then see if it actually looks like what you think. But there's even more cool stuff that can give you a lot of good insight. And that is, Mathematica has a lot of really nice graphics primitives built in. And this is where it totally departs from a static text file. So I'll let you look over the details of this later, but the idea is I'm going to set a certain point size, and I'm going to draw a point on the x-axis whose x value is x of t, where t goes from 0 to 10. And I'm wrapping this all in manipulate here, where t is the value that I'm going to get to change. And so as I play this, you can see that the ball goes back and forth and back and forth. So this is the mass spring damper system. This is the decaying exponential, but you're seeing it in real time here. And I can freeze this, drag this around, and it can give me some better insight. It at least lets me know that there's this is modeling a physical system, which is, after all, what an ODE is supposed to be doing. In the second part of the problem, the students are supposed to calculate the kinetic and potential energies and then plot them out along with the sum. And so, OK, that's pretty easy. You define these functions here, and you can plot them out using the same sort of plot commands that we've been using already. And so this is nice. This is a static plot, and it shows you, that the potential and kinetic energies are trading off, and the total energy in red here is dying away as friction eats away the system. But let's combine that with our previous code to draw the actual physical system, and we'll see what happens. If we wrap this in manipulate, and I play this, I have here not only the mass as it's bouncing back and forth, but also this vertical line is indicating what time we're talking about. And this gives you some really good insight into the problem that you probably wouldn't have. So for instance, here I'll go to a point where, let's see. Here I have the potential energy is essentially 0, and the kinetic energy is very big. And I see that that happens when the spring has pulled the mass so that the mass is right at the origin. The spring is not stretched at all at this point. And that means the potential energy is 0, and the ball is moving sort of as fast as possible. So that's why the potential energy is very small, the kinetic energy is very big. If I move the model a little bit farther, now I'm in a situation where the kinetic energy is 0 and the potential energy is very big. Oh, that's the part where the spring is stretched all the way out and the mass is still. The mass has just finished moving to the left, and now it's going to move to the right. So by wiggling this timeline around and plotting these things, which took just a few lines, I can get a lot of physical insight into what's going on in the problem. I think that's really nice. So in conclusion, you can code more directly. You don't have to do this rigmarole where you translate your problem into a specific format that the tool needs in order to solve the problem. In Mathematica, it was designed to solve these kinds of problems, and so you can just desolve it directly. You can visualize the solutions of your problem in ways that you couldn't do in other programming languages, so that you can get a lot of physical insight. So that's the end of the knowledge section. You can write self-contained homeworks that you can look back on years later. You can code more directly and get a deeper understanding into the problem. Now the last section is power. Now that this is how an engineer, at this point, I would hope that engineering students would say, ah, yes, I see how I can solve my homework with Mathematica. I can get better insight. I can get a better education out of it. But what can I do after college? What can I do besides my homework in Mathematica? Well, there's a website at Wolfram that compares Mathematica in various problem domains to other more specific programs. So for instance, under numerical matrix systems, you could see MATLAB is there. MATLAB was designed as essentially a nice wrapper around a bunch of linear algebra Fortran libraries, and it was designed to do matrix stuff. So there it is under numerical matrix system. In contrast, Mathematica was designed to be a general computation program. Any sort of problem that you might want to use a computer for, Mathematica should be able to help you with. And so you have not only can it solve numerical matrix systems, but also you can you can compile code in different programming languages. You can visualize data in all sorts of elaborate ways, like we were just seeing. You can solve really complicated optimization problems. All of these different problem domains are things that Mathematica can help you with. Here's an example of some newer functionality that I really like. There are all sorts of web APIs built into Mathematica. So for instance, Wikipedia data can grab the text of a Wikipedia article. So I'm a student at UC Santa Barbara, and here's the text from the UC Santa Barbara Wikipedia page. Here's just the first 300 characters. If I take that and I run it through delete stop words, a function which deletes common words like a, an, and the, and then I pass that to this word cloud function, the next thing you know, I'm looking at a picture of a word cloud generated from the text of the Wikipedia page. So I think that's pretty neat. But suppose I wanted to somehow share this with other people. I wanted to distribute this, put this on, host this online somewhere. Well, I can pretty much take the exact same code and wrap it in this form function, and then use a function in the Wolfram language called cloud deploy. And cloud deploy will take this code, package it up, and deploy it to Wolfram Research servers, which then, and what I get back, is a URL. And if I point anybody to this URL, suddenly what they'll be looking at is a form that looks like this that is running on Wolfram Cloud servers. And there's an empty text box here. Now, if I send this URL to my aunt really likes flowers, and she puts in petunia here, it'll run the exact same Wikipedia data code and then the word cloud business on this word instead of UCSB. And she'll be looking at a word cloud from the Petunia Wikipedia page. So in just a couple lines, I have gone from, I have written code that will design a word cloud, will scrape Wikipedia for text, make a word cloud of the text, and deploy it all on somebody else's servers. And I think that is just really cool. In just a few lines of code, you can do that. Here's another example that's close to my heart. So I work in information theory. And at one point, I needed to solve some sort of inequality. I needed to show that as n goes to infinity, this function approaches this other function. And I wasn't sure if that was true or not, if I could actually do that. And so I just decided to plot it up in Mathematica. So here's the Mathematica code that I wrote that fateful day. And I just cranked up n by hand. Nothing fancy going on here, just this line of code and this manipulate. And I could see that the blue lines essentially approached the orange lines. And as it turned out, that it was true. That I showed this to my advisor. He said, great, proof by sliders. You've proven that the blue approaches the orange because you sort of ran it in Mathematica and it seemed to work. And that was very useful. We ended up getting a couple of papers out of that. And here's actually a picture. The green is a plot that I made with Mathematica that essentially is a descendant of the plot I just showed you. And the red is all of the math that we had to do in order to prove that indeed the blue curve goes to the orange curve. So we got a couple of publications out of this. And my point is that if I had to start my research by doing all of this red math here, this very abstract-y math, I never would have been able to figure this out because it's just too much math and it's too abstract. But if I plot it in Mathematica and I drag this little slider around and oh yeah, it looks like the blue goes to the orange, this is the seed for a bunch of later academic results. So that really helped me out personally. And one last example where Mathematica really helped me out was I wanted to go see a musical. I was going to go see a concert, and I wanted to get a good deal because the tickets were pretty expensive. And so I used Mathematica. I had downloaded all of the StubHub ticket data. I was going to buy the tickets on StubHub. And I crunched it with Mathematica, and I had it just using the same kind of manipulate like we've been seeing this whole time. I had it just run essentially a selection on on all of these tickets that I had available so that I could select where do I want to sit in the theater? What's the maximum price that I'm willing to accept? And you would think that StubHub would have this on their website, and you can do some searching of that, but you don't have complete full control over all the ticket data the way that you have if you actually have write a program to do it yourself. And so I was able, with just a few lines of code, in fact, I'll show you the code in a second, to make a nice little GUI where I could actually drill down and say, OK, and do this trade-off myself. What's the trade-off between price and number of tickets available, and how far away am I going to sit in the maximum row? The code to do that is right here. It's pretty short. You pretty much just say things. I mean, this is all very intuitive. If you're looking for exact seats, because not all ticket sellers will sell you the exact seats, if it has the right quantity available, if the price is less than some threshold you set, and you're in the section that you want, not too far away with the row, I want you to select all the tickets that satisfy that criteria, and then show it to me in this nice table view. So this is all the code that was required. I mean, there's more stuff to sort of set up the problem, but to make this GUI, and I got a decent deal on the tickets. OK, so in conclusion, Mathematica is great. You can try it for free. You can try it without even having to install anything. If you use it for homework in your engineering classes, you can express your ideas cleanly and clearly. And it's powerful and useful in college and also in your future engineering careers. So I wish you the best of luck.